Hello, I'm Paul Martin. Thank you for taking the time to view my presentation. My project was on the traveling salesman problem. I am the only member of the team. The traveling salesman problem is the challenge to find the shortest route for a given set of destinations. Typically, routes must start and end at the same point, and every point must be visited exactly once. So part of my motivation was this data set on Kaggle. The dataset contained approximately 200,000 points that were based on the photo of the reindeer shown on the slide. This dataset provided an extremely challenging optimization objective, finding an optimum route for all 200,000 points. For a little background on the importance of this problem, applications include package delivery, DNA sequencing, microchip layout problem, and astronomy. There are many variations on this problem, but the basic premise is the same for all the variations. The traveling salesman problem has been known for many years. It was first mathematically formulated in the 1800s by the Irish mathematician Hamilton. The basic problem asks, what is the shortest possible route? Figure 1 is an example problem with a solution. It shows the destinations as the red dots and the black lines are the routes. Together, all the lines should add up to the shortest route for an optimum solution. The traveling salesman problem is an important problem in theoretical computer science and operations research. It is an NP-hard problem in combinatoric optimization. This means it is not feasible to evaluate for every possible solution for a large number of destinations within a reasonable time limit. The number of combinations increases factorially and explodes exponentially. The challenge with solving the traveling salesman problem with heuristics and algorithms is finding the global minimum. It's likely for large numbers of destinations that the model will become stuck in a local minimum and an optimum global solution will not be found. I looked at a number of possible approaches. Brute force simply looks at every possible solution and selects the shortest route. This solution is not suitable for a large number of destinations. Nearest neighbor selects the nearest point to be added to the route until all points are in the route. Genetic algorithm randomly varies part of the route in an iterative process and accepts improvements on the route as the new solution. K-optimization is an effective method for producing optimum or near optimum solutions for traveling salesman problem, and I'll discuss more on this later. Hill climbing is a general iterative method that starts with an arbitrary solution, then attempts to find a better solution. This approach attempts to avoid local minimums. Lastly, because of the large number of destinations, I decided to use heuristic algorithms and methodologies instead of using exact solver methods. The two optimization algorithm is a simple local search method. The main idea is to uncross any routes that cross over themselves. This is accomplished by reordering sets of pairs until they do not cross. The image to the right is an example of this process. To show how effective this process is, I started with a random route. After only one iteration, the route optimization improved dramatically, and after only 4 iterations, the optimization solution was found. To show how this process works, I made a video with the two optimization algorithm searching for the optimum solution. The dataset starts with a random route of 50 destinations. The threshold for incremental improvement is met through each iteration. The algorithm performs 4 iterations before there is no further improvement. All crossing paths are eliminated until an optimum solution is found. The final model formulation had three main parts. First, the model implements the nearest neighbor algorithm. Second, the model implements the two optimization algorithm. And third, the model uses an incremental improvement threshold to implement the hill climbing technique to avoid a local minimum. Once the threshold is met, the model terminates with its optimum solution. The appearance of the image from the dataset is an indication of the solution's quality. The long routes are artifacts of the nearest neighbor algorithm. Typically with the nearest neighbor algorithm, the last few stages of the route are much greater in length than the first stages. These late stage nearest neighbor artifacts indicate that a more optimum solution exists. While the two optimization algorithm was able to eliminate some long routes, it failed to achieve the best runtime versus solution quality. Despite the nearest neighbor artifacts, the appearance of the image in the dataset indicates a quality solution. It was difficult to achieve a more optimum solution within a reasonable time. Further work could attempt the implementation of a variable optimum algorithm to resolve the compromise between solution quality and runtime. If you would like to view the code for these computational experiments, I have made the notebooks publicly available on Kaggle. Thank you for taking the time to view my presentation.